This is the oral section for the first lab from the group formed by Marc Perez, Xavier Quirapavón, and Abril Marcos. For the section 2.3, we're asked, why do raster plot points align with silent drops in membrane potential? That is because the raster plot documents spikes, which are the points in time where the potential reaches to the threshold, fires, and consequently drops back. That is a spike, and it is the ones that we can see in the plot above. Next up, we're asked, what causes this membrane potential to rise? That would be the input current by the neighboring synapses, which generate an action potential whenever it surpasses the threshold value. Next up, we're asked, why does the potential sometimes decay before reaching maximum value? That is because when the input current is not constant, in that case it is a randomly generated sample, and it arrives in a form of a train of spikes, we can observe short decay periods in the membrane potential of the neuron, which correspond to the interspike periods of the input current. We can see it in a much neater way in the previous example. Here we can see these crest-like patterns forming between each spike.
The input rate follows a Poisson distribution, so it's a random variable. Therefore, the output firing rate is also a random variable. This differs from the previous two sections because since the input was either constant or evenly distributed spikes, then the output could only be a regularly spaced spike train. So when we take a look at the neuronal response curve, we can clearly distinguish three sections. In the first phase, the input rates are way too low to excite any sort of response in the neuron. This is because the RC or tau constant in the membrane potential equation is way too high. So the neuron discharges faster than it can receive the next spike. Therefore, the potential never reaches the threshold potential, so it never gets to fire or do anything basically. And in the next section, you can see that more clearly in the red line is right before it starts to plateau. It's where basically the input firing rate and the output firing rate have an approximately linear relationship in which the more spikes you receive per second, the more you output.
So for the third step of question 2.4, when the input rate is high, as you can observe here, the output firing rate is upper bound by the refractory period of the neuron. That means that it will flatten at 1 over tau rp. This is because the neuron can only fire as often as it can recover. So after a certain point, the input spike frequency doesn't matter. So this is why neurons with longer refractory periods flatten earlier. For example, for this at 17 milliseconds and this one at 10 milliseconds, flatten earlier as their threshold input value is lower. Why do neural firing rates plateau at high input rates? And now again, since the maximum firing rate will be computed as 1 over tau rp, this will lead to a converging plateau at some point in our graphic. This one flattens around 1 over here, and this one will flatten around here. Next question, why do neurons with high time constants plateau earlier than those with low time constants? Since the higher we set the refractory period, the lowest output firing rate we will get. In this case, also again, 1 over tau rp. Thank you for listening us. And that's all. Thank you.